this video, we're going to look at applying derivatives to equation solving using a method called Newton's method.
Hi everybody. In this particular lesson here, what I want to do here is show you something called Newton's method. It's an application of calculus to equation solving, because not every equation that you're going to be asked to solve is going to have a nice, elegant, clean solution. In fact, in most cases out there when we're working with real-world problems, the best we can hope for is a precise answer, maybe not an exact answer. And so we use these things called numerical methods, basically to grind through, and we get an answer that's as close to the actual answer as we can, or maybe even that we just need, right? Maybe there's a level of precision, we're building something and there's a level of precision that I need it to be within, and I can get my answer there even if I don't know the answer exactly. So I'm going to show you how you can use calculus. This is just one method of doing these sorts of problems here. But what I'll do here is I'm going to explain the theory behind this first of all. So let's say that you've got a function here, okay? And let's say, I don't know, it looks something like, something like this. So here's what we're looking for. Sorry, here's our x-axis, here's our y-axis, and we are looking for, let's use green here, this guy right there. That's our root. We are looking to solve the equation here, okay? So this is our y is equal to f of x, that's our function, but we're looking to solve the equation f of x is equal to 0. That's our goal here, okay? And there's our solution right there. So here's what we do. We're going to guess, okay? We're going to guess a solution. Maybe we guess this number right here, okay? Actually, I'll put a little line there. We'll put a little x naught underneath it. And so that's going to correspond to this point right here. And this is going to be our y naught. So the coordinates of that point right there are going to be x naught comma y naught. Now, we guessed that this was our solution, and we're wrong. So what we're going to do here is we're actually going to draw a tangent line to that graph right there. Whoops. That's going to come down. It's going to look like this. There's my tangent line. Now, I'm going to use the calculus I know up to this point to come up with the equation of this particular line. Okay? So I know, for example, that the slope of that red line there, I know that the slope is going to be equal to the derivative of my f of x evaluated at x naught. Okay? So I know that the slope of this line is going to be f primed evaluated at x naught. That's its slope. And I also know that it goes to the point x naught comma y naught. So I know therefore that the equation is going to be y minus y naught will equal f primed at x naught, oops, multiplied by x minus x naught. There's the equation of that red line. Now, notice that where that red line crosses the x-axis is actually closer to the real root than my guess. So what I'm going to do here is I would like to know what this new x-coordinate is. I'm going to call that x1, because that is actually a whole lot closer to the actual answer than my guess. Now, algebraically, how do I find that? Well, algebraically, what I would do is I would set the y-coordinate, okay, because bear in mind, x naught and y naught, those are both the coordinates of that exact point right here, but it's the x and the y are variables. Okay, they stand for any point along that line. So what I'm going to do here is, in order to find out what that x1 is, I'm going to let y go to 0. So I will get 0 minus y naught is equal to f primed at x naught. X, now it's going to be x1. When I solve that, it's going to be x1 minus x naught. Okay? Now, what I'm interested in is figuring out what that x1 is. So this is going to end up being negative y naught equal to f primed at x naught, x1 minus x naught. And again, I'd like an expression for that right here. So what I'm going to do now is I'm going to divide both sides by my derivative. So that'll become negative y naught over f primed at x naught. It's going to equal x1 minus x naught. Now I'm going to clean this up. I'm going to bring that x naught over. So this is going to become x naught minus, now, okay, I will write it like this, and I'm going to clean this up even further here, over f primed at x naught, and that is going to equal my x1. I'm going to clean that up just a little bit more by doing this. X naught minus, now notice that y naught is simply going to be the original function evaluated at x naught over f primed at x naught, and that is going to equal my x1. Perfect. And so what I have here is I've got this new number here, x1, and it is closer to my actual solution than my original guess. But you know what? Maybe that's not good enough. Maybe I'd like a better guess here. So what I'm going to do is I'm going to use this as my starting point. Okay, this is going to come over here. And I'm going to start with this new point. I've got this new point now, x1 comma y1. And I'm going to draw a new tangent line right there. Whoa, look at that. I'm hitting the x-axis right there. This is my new x2. And x2 is a lot closer to my actual root than x1 was, or even x0 was. Now, look at the pattern here. Look at the pattern. If I start this now with x1 here in place of x0 and y0, sorry, y1 in place of y0, and do this whole thing to find x2, I'm going to get the exact same pattern here. So therefore, I'm going to see here that x2 is going to equal x1 minus, f of x1 over f primed of x1. And that's going to create an even better approximation. Well, what if I do this again? Well, if I do this again and using my x2 now as my newest guess, I'm going to get an even better approximation. Let's call that x3. And that'll be equal to x2 minus f of x2 all over f primed of x2. And I can keep doing this, okay? I can keep doing this until that point right there gets so close to that point of intersection, or that root there, that I've either got the exact answer or I've got an answer or an approximation that's so close, it's so precise that it's good enough. For whatever my purposes are, it works. And so what happens here is I create this little pattern here where my xn plus 1, okay, so my last guess, my root there, is equal to the root, or my guess just before it, minus the function evaluated at that guess divided by the derivative evaluated at that particular guess. And if I just apply this rule, so I guess a root, plug it into this little equation, it spits out a better, I guess at the root, it spits out a better guess. Take that, plug it back in, do it again, plug it back in, do it again. See, computers are really, really good at doing that kind of routine. And so you can let this go for as many times as you want. You can investigate the answers to see how close you get, and use that to help you find the roots of equations that might otherwise be quite difficult. Now, we're going to do some examples here, but before we do that, I'm going to take a moment or two just to show you a couple of the pitfalls that you need to be aware of. There are some restrictions on this. I'm just going to show you a handful, and then we'll do some applications here. Okay, so before we go through and start looking at some examples here of how this gets used, just a couple of things to be aware of. There's some scenarios here that make Newton's method, well, where it won't work, at least not the way you'd like it to work. So let me show you an example here. Let's just say that this is my x-axis here, and I've got a function that does something like, let's say this, something like that. So this is the root that I'm, let's say, looking for, And what I do is I start here. So this is my x naught. So it draws its tangent line, and then I look at where the tangent line hits the x-axis, that's right here. So this becomes my x1, goes up, and I draw a new tangent line. And what you see happening here is that this is the root that you find. This is the one that you're looking for, but this is the one that we actually get to. Now, that could have been remedied by simply moving my initial guess closer to my root there. But sometimes you don't know what that's going to look like and where that's going to move. So just be aware that that could happen. Another situation similar to this, okay, again, here's my x-axis. It could look something like this, and you got to watch out for this as well. So let's say that you got your function and it comes down, goes up like this, okay? And so let's say that this is now the root that I'm looking for, but I choose this point right here, let's say, as my initial guess here. So my tangent line spits out a value, oops, well, I maybe didn't draw that exactly as I would have liked it, but my tangent line draws a value and it hits over here, let's say. Here's my x1. And so now I go up here, draw my tangent line, it gets it even closer, and it turns out that even though this is the one that I'm looking for, this is the one that I find. Okay, this is the one that I get closer and closer to. Even though I chose a number that was in fact closer to the root that I was looking for than the one that I found. So that's a possible problematic scenario here. And again, just something to be aware of, that this could possibly happen. Now here's another scenario. So here's the x-axis. We'll just do one more. Let's say that you got a function that looks something like this. I'm going to probably draw this and not do justice to it. See, it comes up, and then it goes like this. Okay, so clearly, this is the root that I'm shooting for right here. It is possible, it is possible that what happens here is you choose, okay, I hope I can draw this. I'm doing this by hand here, so I hope I can draw this to do justice to this. It is possible that you choose this right here, and it draws my tangent line, comes over here, and it goes up, and here's my x1, and then when I draw my tangent line, I'm going to kind of force this to look right. That's actually not too bad. So I choose my x naught. This is my initial guess. Comes down. My initial guess, not guessed. My initial guess. I said it again. My initial guess is x naught. It comes down. I draw my tangent line. It hits the x-axis at x1. I go up, draw my new tangent line, which hits it at x naught. And so what happens here is instead of getting closer and closer and closer to this root, basically I just get a cycle. Okay, and it just goes back and forth, switching values there. Now there are a few other things that that could be an issue when you're using Newton's method, but I tell you what, let's stop looking at the issues here. Let's go through and do a couple of examples and look at how Newton's method works. Okay, so let's use Newton's method here to solve an equation here. We're going to look at solving x squared minus 2 equal to 0. Now, I'm using this right here because I think it's pretty clear. I bring the 2 over, solve, and I'm going to get here that x, well here, maybe we'll write this in red here. I'm going to get that x is going to equal the positive or negative square root of 2. I already know that that's the answer. But let's see what Newton's method does with this. So now, first of all, before I build this, what I got to do here is I need to identify the derivative. So I'm going to need that as part of my expression here. So I know that f primed of x is going to equal 2x. Okay, so Newton's method says that xn plus 1 is going to equal xn minus f of xn over f primed of xn. Okay, so let's plug in our pieces. So xn plus 1 is going to equal xn minus, okay, well the original function here was going to be x squared minus 2, so it's going to be xn squared minus 2 all over 2 xn, the derivative. Now, that is a little messy. Okay, I'm going to try to put this together. I mean, that's really all I need. And if I was to just plug this into my calculator, it's going to be a little messy, but that's all I really need here. But let's clean that up a little bit here. I'm going to got a common denominator here of 2xn. So that's going to be 2xn squared minus xn squared plus 2 all over 2xn. And so what have I got here? I'm going to have x sub n squared plus 2 over 2 sub xn. Whoops, just off the screen there. There you go. And so there's my expression. Okay, so this is my xn plus 1, x sub n plus 1, x sub n plus 1. So starting with my guess, whatever my guess is going to be, I'm going to use this, and that's what I'm going to use to spit out my new guess here. Now, let's take a quick look at what this would look like. Let's say that my 0th guess, my initial guess here, is going to be 1. Okay, well, let's see what that does here. So that means x1 is going to be x naught squared plus 2 over 2 multiplied by x naught. And that is going to be 1 squared plus 2 over 2 times 1. Well, 1 squared is 1 plus 2 is 3 over 2. So my answer here is going to be 3/2. And that becomes my next guess. So x1 is going to equal, sorry, not x1, x2 is going to equal x1 squared plus 2 over 2 multiplied by x1. So it's going to be 3/2 squared plus 2 over 2 multiplied by 3/2. Okay, so now, what have I got here? Well, this is going to end up being 9 quarters, okay? 9 quarters plus 2. Well, 2, in terms of quarters, is going to be 8 quarters. That's going to be 17 quarters divided by 3, or 17 over 12. Now, 17 over 12, let's just think about that for a quick second here. Okay, 17 over 12. Just going to pull out a calculator here and have a quick look so you can see this. 17 divided by 12. Oh, look at that. 1.416. Look at that. Isn't that interesting? What I'm getting there is a number that's actually, it's accurate to about 3 digits. Okay, because remember the square root of 2 is going to be really close to that. Now, if I do this one more time, if I use that 17/12 and plug that in one more time and make my third guess here, okay, is going to equal my, sorry, I got to look at my function again. That was xn squared plus 2 over 2xn. So it's going to be x2 squared plus 2 over 2 multiplied by x2. If I now plug in my 17 over 12 here, it turns out, so this is going to be 17 over 12 squared plus 2 over 2 times 17 over 12. And at this point here, it's starting to get to the point where let's just start using our calculator to get our decimal values. And it turns out our number is going to be 1.41422, okay? Which is correct to 5 figures. 1, 2, 3, 4, 5. It's correct to 5 figures. So we're zeroing in on that square root of 2. And that's how this Newton's method works. Okay, let's take a look at another one. Okay, let's try another one here. So where does y equals x cubed minus x cross the line y equals 1? Now what I'm asking you to do here is essentially solve the equation x cubed minus x equals 1. I'll bring that over so I've got an expression here equal to 0. So I'm looking for, again, where this function, where this function crosses the x-axis, or I'm looking for the roots of this equation. So this is really going to be my f of x here. And so now, what I need is the derivative. So the derivative of this will be 3x squared minus 1. And so now x sub n plus 1 will equal xn minus f of xn over f primed of xn. And now let's plug in our pieces. So xn minus, okay, the original function. Now that's right here. Remember, whoops, I should put equals there. Xn cubed minus xn minus 1 all over 3xn squared minus 1. Okay, so now I'm going to start the process here. Now I could simplify this up a little bit. Actually, I probably should here. Particularly because I've got a cubic here, I've got this quadratic here. So if I go with the same denominator here, xn squared minus 1, when I multiply that by xn here, that's going to be 3xn cubed minus xn minus xn cubed plus xn plus 1. And so that is going to simplify down here. What have I got here? I'm going to have 2xn cubed. My xn's cancel. I've got a plus 1 all over 3xn squared minus 1. Oops. Okay, so there's my expression, okay, for figuring this out these terms here, or at least getting this narrowed in on the root that I'm looking for. Now, let's say that we start with x naught equal to 1. I'm going to show you how you might do this on your calculator here. Okay, I got to make sure I can see my own work here. I'm just going to put 1 in as my answer. And so this is now in the calculator's memory here. So now what I'm going to do, I put parentheses here. This is going to be 2 times my answer cubed. And remember that answer here, I am using second, the negative symbol right there. It's this guy right there. So 2 times my answer cubed plus 1. Whoops. Oh, I hate when I do that. Let's delete. Okay, let's get out of there. 2 times the answer cubed plus 1, close brackets, divided by 3 times that answer squared minus 1. Okay, so now when I press enter, this is going to give me my x1. And I get 1.5 again. Now please don't assume just based on our last 2 examples that that's always the way that works. It doesn't. But now what's fun about this is if I just press second enter, it gives me that expression that I entered in there again. But this time when it refers to the answer, it's going to be referring to this one. So if I press enter now I get this answer here. My second guess is 1.347826087. Let's do it again. Second enter. Ooh. Okay, my third guess is 1.325200399. Okay, let's do it again. Now I'm getting my fourth is 1.324718174. Now I want you to notice what's happened here. And I'm going to do this well, at least a couple more times here. I know that my answer's got this 1 in it. Notice that the first, in the 10th spot here, it seems to have settled in on the 3. The 100th position seems to have settled in on the 2. So little bit by little bit, this decimal is getting clearer and clearer as to what the answer is. If I do this again, second enter, okay, my fifth iteration here is 1.324717957. Well, now that 1.32471 seems to be repeated here. Let's do it again. And my sixth guess here is 1.324717957. Now look at that. They're exactly the same. And if I keep going here, enter, enter, nothing's changing. Now it could be that the change is happening way over here in terms of the decimals, but the calculator doesn't store that many beyond what you're seeing here. So that looks like our answer to what precision are we looking at here? Tenths, hundredths, thousandths, 10,000ths, 100,000, millions. Well, that's more than you would need in most applications there. So I hope that makes sense. That you understand how you can use the calculator to do that, and to get it to whatever degree of precision that you either need or you can get on your calculator here. Let's try one more. Okay, so for this question it says estimate the two zeros of f of x is equal to 2x minus x squared plus 1. Okay, now before I go through and do this, I'm going to take a quick look at this because it does say estimate the two zeros. So what am I exactly looking at here? So I'm just going to go through and take a look at the graph here. Now I could graph this on my calculator, but at the same time I also have a bit of an idea of what this looks like because I can complete the square on that to figure out what this looks like. And as it turns out in this particular case here, this graph is going to have a vertex that's basically 1, 2. It's going to go through a y-intercept there of 1. And so the graph looks something like this. And then it comes back down again and just slightly beyond on the 2 there. And so I'm getting two zeros here, and here. So I'm getting two answers. Okay, well, my function is 2x minus x squared plus 1. I need the derivative to make this work, and so my derivative is going to be 2 minus 2x. So now let's build our little engine here for figuring out roots. So x sub n plus 1 is going to equal xn minus f of xn over f primed of xn. And so that'll be xn minus 2xn minus xn squared plus 1 all over 2 minus 2xn. And let's simplify again. So this will be 2 minus 2xn. This will be 2xn. Remember, I'm going to multiply this by the denominator here. So 2xn minus 2xn squared minus 2xn when I distribute the negative through plus xn squared minus 1. Okay, so what do I got here? I know my denominator is going to be 2 minus 2xn. 2xn minus 2xn, okay, that goes away. Negative 2xn plus xn squared is going to be negative xn squared minus 1. Okay, so there's the tool that I'm going to use to figure out my roots here. Now, I need a starting point. And I am going to end up with two different roots here. So what I'm going to do here is I'm going to let my x naught here, I'm going to start with 0, and maybe over here I'm going to start with 2. And I'm hoping that if I start from here that this will zero in on that particular root, and if I do the process again and start with 2, that'll zero in on that particular root. Okay, so over here I'm going to do this twice here. I'm going to start guessing x naught is going to equal 0. So on my calculator, I'm going to pull this out here. Okay, so I'm going to press 0, so that answer is sitting in there. And then negative answer squared minus 1 divided by 2 minus 2 times the answer. Press enter, and that is going to get me my first guess beyond that. So x1 is going to equal negative 0.5, negative a half. Then I'm going to go second enter, and let's do it again. Well, now we're getting a more interesting number here. So x2, my second guess, is negative 0.41, looks like 6 repeating. Let's do it again. Okay, x3 is going to equal negative 0.4142156863. Let's do it again. x4 is going to equal negative 0.4142135624. Now, I can see kind of where this is going here. So instead of writing out a bunch of these, I'm going to just do this a few more times. Oh, wow. Okay. I was going to do it a few more times and wait and see what it settles in on. But right away, notice what I got here. It didn't change. It didn't change. So I've got that to as precise as I can possibly make it with this calculator. So that's my answer. And then I would round it to whatever the question wanted me to round it to. So there's one answer. And actually that is consistent with what I'm seeing here, although my diagram is a little bit off. My answer is a little bit closer to the center there than it is to the 1, or the negative 1. Oh, wow. I didn't write negative 1 there. Okay, let's go through and do the same thing. But let's start with 2. And actually, once I've got this in my calculator, this is actually a little bit easier, because what I can do now is just press 2, enter. And if I press second enter twice, it pulls up this. And when I press enter, it's going to use 2 as the answer here. So I press enter, and my first guess is going to be 2.5. Second enter, do it again. 2.416, repeating. Do it again. 2.41421566. Do it again. 2.4142135562. Do it again. And just like before, it doesn't take me long. Whoops. Before I've hit a point where I can't get it any more precise than what I've got showing there right now. And so those are the answers that I would be looking for. And again, those are pretty consistent with the diagram that I've got set up. Okay, so that's just a brief introduction to Newton's method. There are other things that we could talk about here, lots of other examples we could do. It turns out that there's even a connection between Newton's method and fractals. Some beautiful, beautiful images can be created if you use Newton's method with complex functions. So anyway, a lot that could be looked at there. I hope this has been helpful.